Welcome back to Hayden's Physiology Channel. We're here. We love America and putting flags on things that we really shouldn't, and especially physiology. Let's start by talking about osmosis, our favorite concept that we all learned about in high school. So osmosis, breaking it down. At its very core, osmosis just means the movement of water across a semi-permeable membrane of water. That being said, there are two relative terms that we associate with osmosis. The root word is something called trophy. Now, if in front of trophy I have hypertrophy, that means my concentration inside, I have one concentration that's greater than the other, and water will move towards this. So water will move towards this. Hypertrophy, water will move away from this. So the whole point of osmosis is to balance out our concentrations. So let's say I had a cell here, and then this is the area around my cell. If this was hypertrophy, or if this was hypertrophy, and then this was hypotrophy, essentially my concentration inside the cell is a lot more than outside my cell. So naturally water is going to move into the cell to not necessarily decrease the number of particles I have, but decrease the concentration of those particles inside my cell. We have another concept called osmolarity. Abbreviated osmol. So again, in osmolarity, we can have hyperosmolarity or hyperosmolarity and hypoosmolarity. Hypoosmol. So this is different than our trophy definitions over here, because these are just relativistic definitions, meaning I can't actually put a measure to this. I have to have one for the other to be measured. With osmolarity, that's actually a real measurement that we can take, called particles over liters. Now, just as a key definition here, this is different than molarity, because molarity is just your concentration of your ion or your concentration of your compound over liters. But when we put ionic compounds inside water, they actually dissociate. So the difference between molarity and osmolarity is that we multiply our molarity by some sort of dissociation constant. If we don't not give it a value, we just assume it's the number of ions that are going to dissociate. Example, NaCl would be 2, because we have sodium and chloride, or the sodium and chloride anion. So again, with hyperosmol, this would mean we have one solution that is more concentrated than another solution. So this one is hyperosmotic to this one, versus this solution is hypoosmotic to this solution. Something to note as well is we don't necessarily, I don't want to say we don't mix them, but these are two independent systems that we're measuring against each other, versus this is all one system and we're talking about how the water is going to move inside this singular system. So where these two concepts of osmolarity and trophy marry, and actually kind of where they get a little bit confusing, is they have relationships. So we could have something that if one solution is hyperosmotic to another solution, and when we put that in our hypoosmotic solution, then our particles are going to balance out and we'll have a net movement of water out of the cell. So example being, if this right here is 300 or say 300 milliosmoles, usually how we measure it. That says 300 milliosmol. and we added our solution was 600 milliosmol. We put that into there. What we're going to get is an increased concentration in our extracellular environment. Now this is assuming that the thing that we're adding is not able to cross the membrane. So that will result in a, let's say this is 300 as well. That will result in a 450 milliosmol and a 300. And these numbers are just estimated. I haven't actually done any math here. But you can see that that would make this environment hypertrophic as well. So when we have a hyperosmotic environment, we also have a hypertrophic environment. There is a different situation when we have something that's isoosmotic, but the thing we're adding is permeable to our cell. So let's say isoosmotic. And let's say it's 300 milliosmol. Again, we have our cell. That is, 300. And outside of our cell is 300. We add this. Cool. So we come through and we add this, and what happens? Well, if this solution has a permeable ion, the thing that's concentrated is permeable, like glucose is a really common example. What we're going to be doing is essentially just adding water, because in this scenario up here, we had our ions or our concentration trapped on the outside. But in this scenario over here, we're going to be maintaining 300 across our whole membrane. So isoosmotic, but we maintain 300, but we still added a bunch of stuff, meaning we added water. So that's going to mean that even our ion can cross, but the water initially does not cross. Which means if it's isoosmotic, that's we just added a bunch of water out here, which now means this is actually going to decrease. It's going to have a net decrease as our permeable ion goes in. Let's say it goes down to 200, and that's actually going to create a hypotrophic environment, and water is going to flow out of our cell. All right, so moving on to a new concept, we're actually going to talk about something called the resting membrane potential. The resting membrane potential talks about this concept of once the electrochemical, it's a big word, electrochemical gradient has been established, we're going to have a difference of charges across a membrane. Say positive, 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 negative, 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 right? So this resting membrane potential is created two ways, or in other words, these charges are allocated in two different ways, because a cell naturally doesn't want to have different charges. If it was up to the cell, it's just going to kind of hang out as a neutral specimen. But we have two mechanisms. I'm going to extend my membrane over here. So first we have something called an ATPase, a sodium potassium ATPase pump. Essentially what this does is it brings in sodium from the extracellular environment. It brings in two of them, but it kicks out, that's potassium, not sodium. It brings in 2 potassium from the extracellular environment, and it kicks out 3 sodium. So we're gonna have a net charge loss every time this thing does its cycle of 1. So for every time this thing goes, we're gaining a whole negative charge. Now there's another part to it. We actually have something inside our membrane called a leak channel. So this thing opens, closes, pushes out, pulls in, pushes out, pulls in. But leak channels are highly specified channels that only allow certain ions to flow through them. This in particular is called a potassium leak channel, K+ leak channel. What that means is once we've established a concentration gradient, the chemical part of our gradient, we have a whole bunch of K+ in here, and we have a whole bunch of Na+ out here. And we've actually already developed some negative characteristic inside our cell to help further develop and sort of solidify the electrical part, or the resting membrane potential, we're going to allow, or rather the driving force is going to cause some potassium to fall out until we hit that final balance of our resting membrane potential. So as far as the degree our resting membrane potential will be, or I guess a better way to say is like how different our charges are going to be, there are a couple factors that influence that. Really the biggest one is going to be, first of all, what is permeable and what's not permeable to our membrane. Without any channels whatsoever, any ion is going to be impermeable. But as we add more channels, whatever specified channel we add, it's going to become, or that ion's going to become more and more permeable. So take these leak channels, for example. If I had way too many of these leak channels, well, just per statistical chance, potassium's going to have a better chance of accidentally falling out of my cell via these leak channels, and that's going to actually increase, or I guess technically decrease, my membrane potential. So let's say we're using the classic example of -70. If I had more leak channels, I might get to a -75 or a -80, or who knows how many leak channels I have, I get to a -100. I don't know. But generally speaking, all ions are insoluble, but the more channels we have, or impermeable, but the more channels we have for those specific ions, the more they become permeable, therefore the more they can cross. If the ion in this scenario, like potassium in this scenario, when it leaves behind more negative characteristic, but the reverse could be true. If we have a driving force that says, hey, say for some reason we had sodium channels that allowed sodium to come in, if sodium became more permeable somehow, that would actually increase or make our resting potential less negative. So the question that everyone is wondering at this point is, why do these ions even want to move? I mean, like, we have positive, think about it. We've created a negative environment here with positive ions. My logic says they should stay put, but no, my logic is wrong. What actually happens is dependent upon a couple factors. So we're going to introduce some really funky vocabulary, and you're going to follow along and you're going to love it. So we have something called the Nernst equation. So instead of writing out this exact equation, I'm going to just rather tell you what the Nernst equation does, because that's a little bit more important than writing out the full equation and then not really understanding what's happening. Nernst equation, what it tells us is, if that ion was isolated in its system and it was the only ion that was totally permeable, that's what the resting membrane potential would be. So example, for potassium, I'm just making a number up, by the way, so don't hold me to this. But let's say potassium had a Nernst value of 100 millivolts. And I'll define this real fast. So Nernst equation, if only this ion were permeable, that would be the resting membrane potential. Okay, so let's say potassium has a Nernst value of 100 millivolts. That means if I left potassium to its free will and it were 100% permeable, then that's what my resting membrane potential of 100 millivolts. Cool. But that's not enough of the story. That's only half. The other part we need to talk about is driving force. This I am going to give you the equation for, because it's much simpler to understand by actually looking at it. So we're going to look at the voltage membrane, or the membrane voltage, meaning what is the actual charge across the membrane, so -70 millivolts, -80 millivolts, and we're going to subtract that from our Nernst value of our ion. In this case, we're using sodium. And we're saying that sodium has a value of 100 millivolts. So let's take a typical cell that has a membrane potential of -70 millivolts, and we are going to subtract that from potassium, which has, in this case, I said is a 100 millivolts, and that's going to get me -110 I should do equals negative 170 millivolts. And boom, I changed some numbers because I realized what I was doing wasn't working. So we actually changed this to a negative 100 millivolts, and then this is also going to be negative 100 millivolts. So we're actually doing negative 70 minus negative 100, which in turn will actually give us a positive value of 30. So positive 30 millivolts. This number, that number specifically, I'm not actually so much worried about the 30 as much as I am about the positive sign. So what we do with this is we're going to place the driving force inside our cell. So we have our cell over here, and remember again we're talking about potassium, and then we have these membranes, the leak channels for the potassium channels, and we have a positive driving force, but guess what? Remember how we said earlier we have our negative charge along the inside of this membrane? That's true, but math tells us that the driving force is actually positive. So that's what we're going to be considering. Positive driving force. What kind of ion is potassium? It's a cation ion. It's a positive ion. So positive repels positive. So that means sodium, which actually ain't no potassium, if it had its way, is going to do exactly that. It's going to want to leave the cell. Here it has its way. Because we're dealing with a positive driving force, potassium is going to want to leave the cell.